You know, we've all seen it in movies, right? Grizzled space miners heading out to asteroids to snag precious metals. But how close are we to that sci-fi future actually, becoming reality? That's what we're going to be diving into today. We've got a whole stack of research here on asteroid mining and this crucial concept, I think it is, called In-Situ Resource Utilization. ISRU.
ISRU.
ISRU. So,
It's a pretty simple idea when you get down to it.
okay.
ISRU is all about using what we find out in space to support our missions
Yeah.
and build things.
Yeah.
Rather than, hauling everything up from Earth
Yeah.
at, enormous expense.
So instead of like launching a water bottle from Earth,
Yeah.
you're saying we could squeeze water out of an asteroid?
Yeah.
I'm having a little trouble wrapping my head around that.
It's wild, yeah.
Yeah.
Yeah, well, picture this. C-type asteroids,
Okay.
which are one of the types that are most likely to contain water, are essentially giant space sponges.
Okay.
They're full of hydrated minerals and clays, thanks to their porous structure, which allows them to trap water molecules.
Okay.
And then you've got icy asteroids,
Uh-huh.
which are literally like a cosmic popsicle.
Right.
They have frozen water
Right.
there beneath the surface.
Okay, so I get that asteroids can contain water,
Yeah.
but how do we actually get it out?
Yeah.
Are we talking about like space drills and giant ice picks?
Well, it's a little more sophisticated than that.
Okay.
The research outlines some pretty fascinating extraction methods.
Okay.
One is thermal desorption,
Okay.
which is essentially baking the asteroid
What?
to release water vapor.
So like a giant space oven.
Yeah, basically.
Doesn't that seem like super energy intensive?
It does require a significant energy source,
Okay.
but the potential payoff is huge.
Uh-huh.
And there are other methods, too, that people are exploring,
Okay.
like microwave heating,
Okay.
which uses targeted microwaves to heat and release the water.
So we've got our space oven and now a space microwave.
Right.
So we've got this water. What do we do with it? Just like slurp it up with a straw.
Not quite.
Okay.
There are a few options. For what we do with that precious H2O,
Okay.
we can store it in super cold tanks.
Right.
For later use,
Hmm.
or split it into hydrogen and oxygen
Mm-hmm.
through electrolysis.
Wait a minute. Hydrogen and oxygen.
Yeah,
Isn't that rocket fuel?
exactly. Think about
Oh,
that.
Okay. Yeah.
Think about the implications. We could create refueling stations right there in space.
Mm.
It would totally change the game for long-duration missions.
Yeah.
Instead of being limited by how much fuel we can launch from Earth,
Right.
we could refuel out in space,
Yeah.
expanding our reach further and further into the solar system.
Okay. That's starting to feel a little less sci-fi
Yeah.
and more like a plausible future. But water is only one piece of the puzzle, right? What about all the materials we need to actually like build things in space? Surely we can't 3D print a space station out of thin air.
Right. Water is just the beginning. And luckily for us, asteroids are also rich in metals.
Okay.
Iron, nickel, cobalt. We're even talking precious metals like platinum and gold.
So it's true that they say there really is a gold rush waiting to happen in space.
There you go.
Where do we even begin to look for these metal-rich asteroids? I mean, are all asteroids created equal in terms of what they have?
They're not all created equal.
Okay.
The research mentions M-type asteroids,
Okay.
which are essentially giant chunks of space ore.
Mm,
They're like prime candidates for metal extraction. They're practically begging to be mined.
that sounds amazing. But how do we get those metals out? Are we talking about like setting up giant asteroid-crushing factories in space?
It might sound like something out of a movie,
Yeah.
but the basic principles are pretty straightforward.
Okay.
One method involves breaking up the asteroid using lasers
Mm,
or mechanical crushers.
okay. So that is the giant space-crushing factory I was picturing.
Sort of, yeah.
Then what?
Well, then we can use something like magnetic separation
Okay.
to extract the iron and nickel.
Hmm.
It's relatively simple, but it's remarkably effective.
Simple is good, especially when we're talking about operating in space.
Absolutely.
But I imagine there are more complex methods as well.
Yeah.
Right.
For extracting other metals, we might use electrostatic separation,
Okay.
which uses charged plates to attract metals based on their conductivity. And for even more complex separations, there's molten regolith electrolysis.
I'm going to be honest, I need a little help with that one. It sounds a little intimidating.
It's basically melting the asteroid dust
Yeah.
and then using electricity to separate out the pure metals. So you end up with pure metals and oxygen as a byproduct.
2-for-1 deals are always welcome, especially in space. So we've got all these raw metals from asteroids. What's next?
Well, we can refine them into usable materials. The research highlights a few different techniques, including carbothermal reduction, and hydrometallurgy. These are essentially different ways of purifying and processing the metals to make them suitable for building things in space.
I'm really starting to see the possibilities here. We can extract water for fuel and life support, mine metals for construction, and process those metals all in space. But how do we put all this together into a functioning system?
That's where ISRU systems come in. And think of them as the infrastructure that makes all of this possible.
So are we talking like giant space factories?
Not necessarily giant factories, although that might be part of the picture eventually. The research points to two main concepts: mobile ISRU units
Okay.
and centralized processing stations.
Okay, break those down for me. What's the difference?
So mobile ISRU units are kind of like robotic miners
Okay.
moving around on an asteroid, extracting and processing resources on site. So imagine a rover equipped with drills, crushers, a mini refinery, all powered by solar panels.
So self-sufficient mining robots
Yeah,
roaming around on asteroids. That's pretty wild. What about the centralized processing stations?
those would be larger facilities, potentially located on a moon or an orbit, where resources from multiple asteroids could be brought for bulk processing and storage.
So it's like building an interplanetary supply chain with asteroids as the mines and these stations as the refineries.
Exactly. And as we scale up our operations, we might even see specialized facilities dedicated to specific tasks, like fuel production or 3D printing of components.
This is all starting to sound like a real possibility, but I have to imagine there are some serious challenges before we're mining asteroids and building stuff in space on a large scale.
Of course, space is a very challenging environment,
Right.
and ISRU is still in its very early stages of development. There are technical hurdles, safety concerns, a whole host of unknowns to contend with.
Like what are some of the biggest challenges facing ISRU?
Well, for starters, we need to know what we're working with,
Yeah.
right? It's not like we can just land on any asteroid and start digging.
Right.
We need detailed maps and analyses
Mm.
to identify the right asteroids
Yeah.
with the resources we need.
Makes sense. What else?
Energy is a major concern.
Yep.
Powering all this equipment, especially in deep space, is going to require some innovative solutions. We might need to develop new types of solar panels, nuclear reactors, or even tap into the energy of the asteroid itself.
Okay, so power is a big one. What
Yeah.
about the equipment itself?
Well, our equipment needs to be incredibly robust.
Yeah.
We're talking extreme temperatures, radiation, micrometeoroids. Space is a harsh mistress. So building machines that can withstand these conditions for long periods is a significant engineering challenge. And then, of course, there's the cost.
Cost is always a factor, especially when you're talking about space exploration.
Absolutely. Developing and deploying these ISRU systems is going to require a significant investment. But you can think of it as an investment in our future.
An investment in a future where we're not limited to Earth's resources, where we
Yeah.
can build and explore freely in space.
Exactly.
It's a pretty compelling vision. But what does that future actually look like? What are the long-term trends shaping the development of ISRU?
That's a great question, and one that deserves further exploration.
Okay.
We're going to delve into the future of ISRU, exploring some of the most exciting trends and breakthroughs
Sounds good.
right after this.
Oh.
Let's go.
So we left off talking about some of the major hurdles facing ISRU, accurately identifying those resource-rich asteroids, powering everything up in deep space, building equipment tough enough to handle that unforgiving environment. It sounds like a pretty daunting task.
It is. It definitely is.
Okay.
But the challenges of today often become the breakthroughs of tomorrow. The research points to some pretty exciting future trends that could revolutionize how we approach ISRU.
Okay. Let's hear about these trends. What's on the horizon? That could make all this asteroid mining and space construction a reality.
One trend that really stands out is the development of autonomous systems. We're talking AI-powered robots, capable of handling a lot of the tasks involved in ISRU, from prospecting and mining to processing, even construction.
So instead of sending humans to do the dirty work in a dangerous environment, we're sending robots. That makes sense. But can we really trust robots to handle such complex tasks, especially in the harsh conditions of space?
That's a valid question, and it's one that researchers are actively addressing. These aren't your average robots. We're talking about highly sophisticated systems equipped with advanced sensors, machine learning algorithms, and the ability to adapt to unforeseen circumstances. Think of them as the next generation of Mars rovers, but with a much broader skill set.
I'm picturing a swarm of robot miners scurrying around on asteroids, digging, crushing, refining metals. It's both fascinating and a little unnerving. What are the advantages of using autonomous systems for ISRU?
The advantages are numerous. First and foremost, it significantly reduces the risk to human life. We can
Yeah.
send robots to explore and work in hazardous environments without putting astronauts in harm's way.
That's a big one, especially when you consider the dangers of radiation, micrometeoroids, and just the unpredictable nature of space. What else?
Autonomous systems can also work tirelessly without needing sleep, food, or breaks. They can operate continuously, maximizing efficiency and productivity.
So robots are more efficient and don't need vacations. I can see why this is an attractive option for space exploration. Are there any other trends shaping the future of ISRU?
Another really fascinating concept is multi-asteroid operations.
Okay.
We've talked about different types of asteroids containing different resources. Some are rich in water, others in metals. Still others might contain valuable volatiles like helium-3.
So instead of searching for one asteroid that has everything we need,
Right.
we could coordinate mining operations across multiple asteroids.
Precisely. Imagine an interplanetary supply chain with specialized mining outposts on different asteroids, each extracting specific resources. Those resources could then be transported to wherever they're needed, a lunar base, a Martian settlement, even a space station in orbit.
It sounds incredibly complex. How would we even begin to coordinate something like that?
It would require advanced planning, sophisticated logistics, and a really robust communication network. But the benefits of such a system are immense. It would allow us to access a much wider range of resources and make our space operations more resilient.
Resilient in what way?
If one mining operation encounters a problem, say a technical malfunction, or an unexpected asteroid event, we'd have other sources to rely on. We wouldn't be putting all our eggs in one cosmic basket, so to speak.
That makes a lot of sense. We've talked about robot miners and an interplanetary supply chain. Is there anything else on the horizon that could revolutionize ISRU?
The research also highlights the development of advanced material processing techniques. We've discussed some basic methods, like molten regolith electrolysis and carbothermal reduction. But the future holds even more exciting possibilities.
Like what?
Imagine taking those raw materials, extracted from asteroids, and creating entirely new alloys and composites, materials with properties specifically tailored for the challenges of space.
Okay, you're going to have to break that down for me. What kind of properties are we talking about? And how would these new materials benefit space exploration?
Think about the extreme conditions in space: microgravity, radiation, extreme temperature swings. These conditions can actually influence the properties of materials in ways we're only beginning to understand. By processing and refining materials in space, we could create materials that are stronger, lighter, more durable, more radiation resistant than anything we can produce on Earth.
So we're not just talking about using asteroid metals to build things. We're talking about creating entirely new materials.
With unprecedented properties.
Exactly. These advanced materials could revolutionize how we build everything, from spacecraft and habitats to solar panels and scientific instruments.
Give me some examples. What could we create with these space-age materials? Imagine super strong, lightweight alloys for constructing vast space stations, or interplanetary spacecraft, or radiation shielding composites for protecting habitats and astronauts from the harmful effects of cosmic rays. We could even develop self-healing materials that can repair damage from micrometeoroids, essentially making our structures more resilient, less prone to catastrophic failure.
That sounds like something straight out of a science fiction novel.
It does.
But how far off are we from actually seeing these advanced materials become a reality?
Well, the research doesn't provide specific timelines, but it's clear that there's a lot of research and development happening in this area. Scientists and engineers are pushing the boundaries of material science, exploring new processing techniques, experimenting with different combinations of asteroid-derived elements with the increasing interest in space exploration and commercialization. I think it's safe to say that these advancements will only accelerate in the coming years.
It's exciting to think about the possibilities. But with all this talk about robots and advanced materials, it's easy to forget that there's a human element to all of this. What role will humans play in this future of asteroid mining and space construction?
That's a good point. Wall automation will undoubtedly play a significant role in ISRU. Humans will still be essential. We'll need engineers to design and build these complex systems, scientists to analyze and characterize the resources, technicians to operate and maintain the equipment, and mission controllers to oversee everything from a distance.
So it's not just about robots taking over.
Not at all. Humans will still be at the helm, But their roles will evolve. We'll need people who are skilled in robotics, artificial intelligence, remote sensing, and data analysis. And as we establish a more permanent presence in space, we'll also need people with expertise in habitat construction, resource management, closed-loop life support systems, even space law.
It sounds like we're talking about a whole new generation of space pioneers, people with a unique blend of technical skills and the ability to adapt to the challenges of living and working in space.
Absolutely. And as we venture further into the cosmos, those human qualities, ingenuity, adaptability, resilience, and the thirst for exploration will be just as important as the technology we develop.
Well said. This deep dive has been incredibly insightful. We've gone from the basics of extracting water and metals to exploring a future of robot miners, interplanetary supply chains, and advanced materials that sound like something straight out of a sci-fi movie. It's clear that ISRU has the potential to completely revolutionize how we explore and utilize space.
I completely agree. And while there are certainly challenges ahead, the progress being made in this field is truly inspiring. It's an exciting time to be following the developments in space exploration.
It certainly is. We've covered a lot of ground in this deep dive, but there's one crucial aspect we haven't touched on yet: the economic and societal implications of asteroid mining and ISRU. That's a whole other can of worms, and we'll be opening it up right after
that. We've been on this journey, exploring the how-to of asteroid mining and ISRU, the water extraction, the metal refining, the robot miners, even those crazy new materials. But now I'm kind of curious about the bigger picture. What are the economic and societal implications of all this? Like, how does it change things here on Earth?
Yeah, that's an important question, and one that the research kind of only touches on briefly. I mean, right now we're still in the early stages of, ISRU development, but it's not too early to start thinking about those potential impacts, both the positive and the negative.
So let's start with the positive. What are some of the potential economic benefits of asteroid mining?
Well, the most obvious benefit is access to vast, new resources. I mean, we're talking about trillions of dollars worth of metals, water, and other valuable materials just floating around out there in the solar system.
That's a lot of potential wealth just waiting to be tapped. But how does that translate into real-world economic benefits? Well, for starters, it could significantly lower the cost of space exploration and development. I mean, right now, launching materials from Earth, it's incredibly expensive.
Right.
By using resources found in space,
Yeah.
we could build and operate in space a lot more efficiently, opening up, new possibilities for research, exploration, even commercial ventures.
So it's like bootstrapping our way into space.
Exactly. And as the cost of accessing space decreases, we could see this whole new wave of innovation, entrepreneurship, similar to what happened with the internet back in the early days.
I can see that. Suddenly, space isn't just for governments and megacorporations. It becomes accessible to startups, researchers, even just individuals with big dreams.
Precisely. And that increased access could lead to just a boom in new technologies, new industries, creating jobs, stimulating economic growth here on Earth.
So we're talking about like a whole space economy. With asteroids as the raw material suppliers, that's pretty mind-blowing. But are there any potential downsides to all this?
Of course. I mean, no technological advancement comes without potential risks and challenges.
Right.
One concern is the impact on existing industries.
I see what you mean. Like if we start mining platinum and other valuable metals from asteroids, what happens to the mining companies and workers here on Earth?
It's a valid concern, and one that we need to address proactively. It's likely that asteroid mining will disrupt some existing industries, but it could also create opportunities for new ones. We might see a shift in focus from terrestrial mining to space-based resource extraction and processing, requiring new skills, new expertise.
So it's not necessarily a loss of jobs, but a shift in the types of jobs available.
Exactly. And that shift could ultimately be beneficial, leading to higher paying or specialized jobs in this burgeoning space economy.
That makes sense. Are there any other potential downsides we should be thinking about?
Another concern is the potential for conflict and competition. Right now, there aren't any really clear international laws or regulations governing asteroid mining.
So it's a bit of a free-for-all.
In a way, yeah. And as the technology matures and those economic stakes rise, we could see nations or corporations, vying for control of the most resource-rich asteroids.
That sounds like a recipe for trouble.
It could be. That's why it's so crucial that we start developing a really robust legal framework for space resource utilization, one that ensures, fair and equitable access, prevents environmental damage, and promotes peaceful cooperation.
So we need like a kind of space law, similar to international maritime law?
Precisely. We need to establish clear guidelines for prospecting, claiming, and extracting resources from asteroids, as well as mechanisms for resolving disputes, and ensuring that the benefits of space mining are shared, equitably, among all nations.
It sounds like a daunting task, but also an essential one if we want to avoid conflict and make sure that asteroid mining benefits all of humanity, not just a select few.
I couldn't agree more. And it's not just about avoiding conflict. We also need to be really mindful of the potential environmental impacts of asteroid mining.
That's actually something I hadn't really considered. How could asteroid mining harm the environment, especially when we're talking about, the vastness of space?
Well, while space might seem empty, it's not exactly a pristine wilderness. Asteroids themselves could have unique ecosystems, scientific value, and, our mining operations could create debris fields, disrupt the orbits of other celestial bodies, or even contaminate pristine environments on other planets or moons.
So it's not just about what we take from space, but also about the potential harm we could inflict.
Exactly. We need to develop sustainable practices that minimize our environmental footprint and ensure that we're not damaging these, celestial environments for future generations.
That sounds like a tall order. Are there any examples of how we could mine asteroids sustainably?
Sure. One approach is to focus on extracting resources from near-Earth asteroids, minimizing the distance we have to travel, reducing the energy required for transportation. We could also explore ways to capture and reuse any debris created during mining operations, preventing it from becoming a hazard to other spacecraft or celestial bodies. And, we need to prioritize scientific research and exploration, making sure that we really understand these environments before we start exploiting them.
It's all about finding that balance.
Right.
Balancing the economic potential of asteroid mining with the need to protect the environment and ensure equitable access for all.
It is, and that's why these conversations are so important. We need to start thinking about these issues now, while the industry is still in its infancy, so that we can shape its development in a way that benefits all of humanity.
It's been really incredible, this whole journey, exploring the science, the technology, and now the ethical and societal implications of asteroid mining. It's clear that ISRU has the potential to just completely reshape our relationship with space, opening up new frontiers for exploration, innovation, and economic growth.
I completely agree. And while there are certainly challenges ahead, the possibilities are truly inspiring. It's a good reminder that we're not limited by the confines of our planet, that our future lies among the stars.
And on that note, we've reached the end of our deep dive into asteroid mining and ISRU. We hope you've enjoyed this journey through the frontiers of space, and the challenges and opportunities that lie ahead.
As always, we encourage you to keep exploring, keep learning, and keep asking those big questions, because the future of space is in our hands, and it's up to all of us to shape it, wisely and responsibly.
Thank you for joining us on this deep dive. Until next time, keep looking up and keep exploring.